Hi, I'm Professor Goins. Welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in college mathematics, you're in the right spot, so go ahead and click the subscribe button. That said, let's get into the current video. I'm going to take a look at finding the arc length for a parabola, and of course I mean by a section of a parabola, because otherwise it'd be infinitely long. To remind you, the arc length for a curve, so let me go ahead and again just get a general graph here. If I have a graph of, say, y equal to f of x on an interval from, let's say, a to b. If I want to compute the length of that curve, we have a formula for it, and this is the integral from a to b of the square root 1 plus the square of the derivative dx. In a previous video, I showed where that formula comes from, so if you're not sure, if you haven't seen that before, go ahead and watch that. But for this video, we just need to use it. Okay, so for example, I'm going to, again, look at a portion of a parabola. Now, let's say I've got, say, y equal to x squared, and this is sort of the basic parabola here. Now, remember, when I take this and I plug it into this formula, I have to differentiate and then square it. So what I'm going to do, if I differentiate this, I get 2x, and then I square it, I'm going to get 4x squared. And that doesn't really make the computation that much more challenging, but I want to try to make the computation of the integral as clean as possible. So I'm going to clean this up a little bit, and I'm going to say, let's compute the arc length for x squared over 2, because notice when I differentiate that, I'm going to get x, and then the derivative squared would be x squared. So we'll just kind of clean that constant up. And this will then generalize to any parabola, because any parabola can be written in standard form, which is, of course, a times x minus h squared plus k. And then with a u substitution, it would just be a and then, say, u squared, say, plus k. But then the derivative of a constant would go away, and then it would just basically be a u squared. So then again, I could, differentiate and get a function very similar to this one. Okay, so really this is going to generalize to any parabola, but in particular we'll do x squared over 2, since the square of the derivative will be as clean as possible. And let's go from, let's say, 0 to 1. Okay. All right. So let's go ahead and compute. So I'll set it up as a formal example here. For f of x equals 1/2 x squared on the interval from 0 to 1, compute the length of the curve. Okay, so solution. Well, let's see. The length is going to be the integral from 0 to 1 of the square root of 1 plus. Now, of course, we've got the formula written over here, so I differentiate and then square it. And of course, the derivative of 1/2 times x squared. Let's just show all the details here. It would be 1/2 times 2 to the x to the first, right, using the power rule for derivatives. And of course, 1/2 times 2 is 1. X to the first squared would be x squared. So I get the integral from 0 to 1, square root 1 plus x squared dx. Okay. Now, arc length is generally introduced in probably the second chapter, could be the first chapter of a Calc 2 course. And some of the integration techniques are generally introduced after. And of course, different courses might order things slightly differently, but generally speaking, when you do arc length, it's before trig substitution, so you would not be able to compute this integral. And again, this is just for a very simple parabola. But once you learn how to do trig substitution in your trig integration or trig technique chapter, integration technique chapter, you can compute this one. Of course, this one is a trig substitution with the tangent function. So x is going to be tangent theta, and so dx is then going to be secant squared theta d theta. All right, so I'll go ahead and plug those in. And again, when we go from, say, an algebraic integrand to a trig integrand, we usually leave off the limits of integration, and then we kind of convert back to the original variable in the end, which is what I'll do. So this would be the integral from something to something. We'll leave that off. And this would be the square root of 1 plus x squared, so that'd be tangent squared theta. And then dx is secant squared theta d theta. Now, 1 plus tan squared, using Pythagorean identity, is the same thing as secant squared. Therefore, my integrand becomes the square root of secant squared theta, and then times secant squared theta d theta. And in this case, this does actually reduce, right? When you take the square root of a square, you do have to replace that. Sort of the algebraic simplification would be the absolute value of what's inside. But we can verify, and again, it's just going to make this video super long, so I'm just going to leave that part off. But this does reduce to the secant of theta. So I have integral of secant of theta, secant squared of theta, d theta. And then that becomes secant cubed. Now I'm going to make a quick comment over here. I did kind of leave that part off. If you do want to see a verification for that, comment below and I'll create another video showing the verification that the square root of the secant squared is the secant theta without the absolute value bars. All right, so now I've got the integral of secant cubed. And this is one that I think Van Hamlin had posted a long time ago, how to integrate secant cubed. So if you've seen that, if you know how to integrate this, you can fast forward through the next portion here, but I'm going to go through and actually show all the details for integrating secant cubed, just so this video is complete. Okay, so in order to integrate secant cubed, well, I'm actually going to rewrite this in the same thing that the previous step had. I'm going to rewrite this as the integral of secant of theta, secant squared theta, d theta. And what integration technique would apply to this? Well, let's think about this. I got these two factors here, secant of theta and secant squared theta. Secant of theta we can differentiate, and secant squared theta we know an antiderivative for. Well, that kind of tells me that integration by parts would be applicable, because remember, when you do integration by parts, we have to rewrite the entire, or we have to decompose this entire expression here after the integral sign as the product of u and dv, one of which we differentiate, one of which we take an antiderivative for. So again, as long as we kind of recognize that, we see that integration by parts is going to be the way to go. And as I already mentioned, secant squared we know an antiderivative for, secant we know a derivative for. So therefore, that already tells me what my choice is going to be. dv is going to be secant squared theta d theta. Therefore, the antiderivative would be tangent of theta. U, of course, is secant of theta. Differentiate that, we get secant of theta, tangent of theta, sorry, I kind of squeezed this in here, and then times d theta. All right, then integration by parts. Formula says that this is going to be uv, so in other words, secant theta, tangent of theta, minus the integral of v du, so tan theta, secant tangent, d theta. And then what I'm going to do is let's put the tangents together. So secant theta, tangent theta, minus the integral of secant squared times tangent squared. Now what do I do with that? Well, tan squared, we can use a Pythagorean identity on that. So let's see, I want to leave up some of this work. Let me see. I'm going to leave the original trig substitution up here. So let me just kind of box this off so I don't accidentally erase it. Watching me do it anyway. So let me go ahead and clean this part up. Okay, don't erase, don't erase. All right, so let's leave that again because we'll need that when we go from the theta antiderivative back to an x antiderivative. All right. Now, what do we do with this integral? Well, there's a Pythagorean identity that I've already used. I don't know that I wrote it up here, but we used the tangent squared plus 1 is secant squared. So let's go ahead and plug that in here. And we get, this is equal to, oh, wrong color. We get this is equal to the, a little more ink here in this marker here. So secant tangent minus the integral of secant of theta times, now remember, we're at the identity over here, remember tan squared plus 1 is secant squared theta. If you forgot that, just use the base Pythagorean identity, so sine squared plus cosine squared theta is 1. And then how do I go from here to here? Well, all I have to do is multiply the entire equation through. Well, how do I go from sine squared to a tan squared, right? I have to have a cosine squared in the denominator. So what I do is I multiply the entire thing by the reciprocal of cosine squared. So therefore, sine squared over cosine squared is tan squared. Cosine squared over cosine squared is 1. 1 over cosine squared would be secant squared. So again, really this is the only one that you have to memorize, and then the other Pythagorean identities just stem from that. Now, notice I've got tan squared in my integrand, so what I'll do is I'll take this and I'll solve it for tan squared, meaning I get secant squared minus 1. And then d theta. All right, so let me go ahead and clean this up. Again, let me leave the original trig sub right here. And then what do we do? Well, let's distribute secant through that. So I get the, again, the secant tangent out front minus the integral of. So I'm going to do two things. I'm going to distribute secant of theta through the parentheses. And then since there's going to be two terms in this integral, I'm also going to separate the integral. So minus the integral of secant cubed theta, and then d theta. Then it would be minus secant, but then I'd have minus with a minus, so this would be plus the integral of secant of theta d theta. Okay. Now, let's look where we are here, because it kind of looks like maybe we're just spiraling out of control. Well, we're not, because remember that at the beginning of the string of equalities, we started with the integral of secant cubed. And on the other side of the equal to sign, we have another integral of secant cubed. So we get this repeated integral. Well, I'm trying to solve for this, right? I'm trying to compute that, or solve for it. And what I could do is I could take this term and just add it to the other side. And that would give me, so let's kind of summarize here. I've got twice the integral of secant cubed theta d theta is equal to secant of theta, tangent of theta, and then this would be plus the integral of secant of theta d theta. Okay. So we're very close. All we need to be able to do is then just find the integral of secant of theta. Okay, so now we need to compute this integral. So let's go ahead and do that. So let's, so now compute the integral of secant of theta d theta. Okay. And this one is going to be a little bit of work as well. This one is going to be, so the way that I'm going to do this is I'm going to first and foremost rewrite secant of theta as 1 over the cosine of theta. All right, this is the reciprocal definition of the secant. And then what I'm going to do with 1 over cosine is let's multiply top and bottom by cosine. So this is the same thing as cosine theta over cosine squared theta. Using a Pythagorean identity again, I can write this as cosine of theta over, or I don't have it written up here anymore, but remember it was sine squared plus cosine squared is 1. So if I subtract sine squared, cosine squared is the same thing as 1 minus sine squared theta d theta. All right, and then what do I do with that? Well, let's see. It looks like I can use a u substitution there. So I get u is equal to sine of theta. Then du is equal to the cosine of theta d theta. All right, I go ahead and plug that into that integral. This is going to be equal to 1 over 1 minus u squared du. If that happened to be a plus, then it would be an inverse tangent, but it's not, so it's a minus. So therefore, the way we'd integrate this, well, I need to factor this and then use partial fractions. So integral of 1 over 1 plus u, 1 minus u, du. All right? So now let's do the partial fraction decomposition of that. So remember that the partial fraction decomposition, in the case where the denominator consists of distinct linear factors, well, the possible denominators that we would have added together is just going to be each of the individual denominators, so 1 plus u and 1 minus u. What's on top is an unknown constant, so a and b. Now what I'm going to do is clear the denominators and get what I refer to in class as, say, the coefficient equation, because it's the equation from which we obtain the coefficients. I multiply both sides by this denominator, and I get a times 1 minus u plus b times 1 plus u. Okay? And then what we do is we choose appropriate values, or what I refer to as convenient values of u, in order to solve for a and b. Now, any choice of u would work, but there's a couple that are going to make our lives easier. For example, 1 and negative 1. So if u is equal to 1, what happens is this term zeroes out, right? It's going to be a times 0 plus b times 2. Therefore, the coefficient b is 1/2. Okay? And then coming over here, let's choose, of course, the other convenient value for u is negative 1. So if u is negative 1, we get 1 is equal to a times, so it's 1 minus negative 1 plus b times 0. And of course, 1 minus negative 1 is 2. This part's 0, so this is 1 equals 2a, which says that a is equal to 1/2. All right, now I can go back to this integral here, my u integral, and this is equal to integral of a over 1 plus u, so 1/2 over 1 plus u, and then plus, b was 1/2, so it's 1/2 over 1 minus u du. In each of those terms, we can find an antiderivative for it. These would each be natural logs. So I have 1/2 natural log of absolute value of 1 plus u plus 1/2 natural log absolute value of 1 minus u. Now the way I have it written here is an indefinite integral. So I'm going to leave off the plus c because I know I'm going to turn this into a definite integral in the end, if we ever get there. All right, so let's see, where were we? This was the integral of secant cubed. No, I'm sorry, integral of secant. And remember that we need to go back to the variable theta. So u was given by sine of theta. So this is equal to 1/2 natural log absolute value of 1 plus sine of theta plus 1/2 natural log absolute value of 1 minus sine theta. All right. Now this was, remember, this was the integral of secant of theta, and that was only part of my overall theta antiderivative. So let's kind of put all this together then. Remember, what we were ultimately computing was the arc length for that section of a parabola. So remember that this was equal to, so let me kind of summarize a bunch of things here since it's been a while since we were at the beginning. This was the integral from 0 to 1, the square root of 1 plus x squared dx. Remember, this was equal to the arc length of x squared over 2 and 0 to 1. Well, we found that this turned into the integral of secant cubed theta d theta using a trig substitution. Now, when we did the trying to remember exactly what we had here. When we had the integral of secant cubed, remember we had 2 of those, and then because we had a repeated integral, we divided by that, so I've got 1/2 secant of theta tangent of theta, and then it was plus the integral of secant of theta d theta, and we just found the integral of secant was this. So therefore this is equal to 1/2 secant of theta tangent of theta plus 1/2 natural log absolute 1 plus sine theta plus 1/2 natural log absolute 1 minus sine theta. And now we have to go from theta back to the original variable, which was x. And again, this right here was our trig substitution. That's the relationship between x and theta. All right, so now we need to take that theta antiderivative and turn it into an expression with x's in it, and then evaluate from 0 to 1. Let's go ahead and do that. Well, from x equals tan theta, we can create a reference triangle. Right? And remember, looks like that marker might be running out of ink here. Hopefully that shows up. So x equals tan theta. Of course, tangent is a ratio of sides, so I can write this as x over 1. And tangent, of course, is opposite over adjacent, so that would be opposite over adjacent. And then using the Pythagorean theorem, the hypotenuse would be the square root of 1 plus x squared. Of course, that was the expression that appeared in this original integral. All right, well, we need the secant, the tangent, and the sine of theta. All right, well, let's go ahead and do that. Of course, we already had tangent, but just for completeness here, or just for organizational purposes, the tangent of theta is x. The sine of theta, remember sine is the SOH part of SOHCAHTOA, right? So it's opposite over hypotenuse. So it'd be opposite over the hypotenuse, right? And we also need the secant. So the secant of an angle, remember, is the reciprocal of the cosine of an angle. And the cosine of an angle is adjacent over hypotenuse. So therefore, this would be, the secant would be the reciprocal of that. So instead of, so let me just abbreviate here, 1 over, instead of adjacent over hypotenuse, it would be hypotenuse over adjacent. And of course, that would be the square root of 1 plus x squared. Okay, now we can finally put all this together and finally compute the arc length of that very simple parabola. Okay, so therefore the length is 1/2 times the secant. So the secant was this, so square root of 1 plus x squared times the tangent, which was x, plus 1/2 the natural log absolute value of 1 plus the sine of the angle, which was this expression here, so x over square root 1 plus x squared, plus 1/2 natural log absolute 1 minus that same expression, so x over square root 1 plus x squared. And this is kind of starting to run together here, so let me get rid of that part. And we evaluate from 0 to 1. All right, we go ahead and let's plug 1 in. If I plug 1 in, 1 plus x squared would be 2, so I'd have root 2 over 2, and this is 1, so that's root 2 over 2. Plug 1 in here. This would be plus 1/2 natural log of, well, let's just write it out, 1 plus 1 over root 2, plus 1/2 natural log of 1 minus 1 over root 2. So this is what I get when I evaluate the x antiderivative at the upper limit of integration. And then we will subtract what I get when I plug it in the lower limit of integration. So minus, let me use a big square bracket here just so I can distinguish off what I get when I plug in 0. Plug 0 into this, that's going to be 0. Plug 0 into this, I'm going to get plus 1/2 the natural log of, well, this would be 0, so I get the natural log of 1. I'll just put 1 plus 0. And then here I get plus 1/2 natural log absolute value 1 minus 0. Now let's look at the terms within the big square brackets. 1 plus 0 is 1. Natural log of 1 is 0. So that'd be the 0 here as well. So therefore this whole part here within the second square brackets becomes 0. All right, so therefore the arc length is given by, we could of course write this as 1 fraction and write this as 1 fraction, but I'm just going to leave it like this. This would be the exact arc length of x squared over 2 on the interval from 0 to 1. And once again, you could generalize by completing the square, put any quadratic in standard form, and then with a u substitution, you just get a constant times u squared, and therefore the computation would be very, very similar. Thank you for watching, and please consider subscribing.